Hello everyone, this is Dr. Hopkins with our next in our series of videos where we're going to discuss a new topic. It's not going to be buffers. It's oxidation and reduction, which is abbreviated, oddly enough, as redox, not ox-red. So let's review, I think, and this is probably something you learned in high school or you learned last semester, but the definitions of oxidation and reduction. Oxidation is basically the loss of electrons by a substance. Reduction is just the gain of electrons by a substance. An example of oxidation is if we have metallic sodium, it loses an electron, undergoes an oxidation to sodium plus, the form we typically find. That's an oxidation. If we have chlorine, Cl, we add an electron or reduce, it gets reduced, gains an electron to Cl minus. So that's an example of a reduction. So in order to be completely confusing, something that gets oxidized is often called a reducing agent. Something that is reduced is called an oxidizing agent. And the reason that is that you can't have an oxidation without a corresponding reduction. Okay, so it's kind of like acids and bases. An acid without a base, you can't have an oxidation without a reduction. So you have to have an oxidizing agent and a reducing agent in each case. So a redox reaction is oxidation reduction, where our reactants are actually supposed to be reduced and oxidized, and you form products. Now I'm going to note in this course, it's beyond the scope of this class to predict products. Now, unlike our acid-base in some of our precipitation cases, where we can ask you to predict products, you can do that. You can't actually do that in redox reactions. So here's an example. What we're going to do is we're going to identify them, though. So we have iron, solid, and then oxygen, and this is the kind of classic redox process where you form rust. Okay, so iron oxide, excuse me. And in this case, the iron is being oxidized. In a traditional sense, it's actually picking up oxygen comes from, but it's actually going from an iron where it's iron metal to an iron 2 plus oxidation state. And then our oxygen is undergoing a 2-electron reduction. So we have a 2-electron oxidation of iron, a 2-electron reduction of oxygen, forming iron oxide. So the question is, how do we decide what's being oxidized and reduced? We're going to introduce an accounting system to track these redox electrons. And that's based on oxidation numbers. Now, an oxidation number is not a real charge, doesn't really exist, but it's the charge that ion or that atom would be if it were a monoatomic ion in the compound. Okay, so it's kind of going around in circles, but that's the reason why it's a hypothetical charge. And it's mostly just to keep track of what's getting electrons and what's losing electrons, or what's being oxidized and reduced. So our rules, we have some rules for assigning oxidation numbers. If your atom's in the elemental state, the oxidation number is 0. Okay, so for most of the elements on the table, that's just the solid that it is. So iron, sodium, they were all oxidation number 0. But remember, there are some that are elemental diatomics, O2 and H2. In those cases, the O2 is equal to 0, the H2 is equal to 0. If you have a monatomic ion, the actual charge is the oxidation number. In that case, that's the one case where the oxidation number is a real charge. But so if you have iron 3 plus dissolved in water, the oxidation number is +3, or in this case, iron 2 plus, it's +2. And then when you have a compound or a polyatomic ion, there are some kind of rules to help establish the oxidation numbers of everything in that polyatomic ion. So in almost every case, oxygen has an oxidation number of -2. The only exception is when oxygen is in a peroxide. That's an O2 2-. In that case, it's a -1. But peroxides are pretty rare. We're not going to use them very often. And then hydrogen, when it's bonded to a nonmetal like fluorine or chlorine or one of the elements on the right-hand side of the table, it always has an oxidation number of +1. If hydrogen's bonded to a metal, it has an oxidation number of -1. That's when it's acting like a hydride. And then fluorine always has an oxidation number of -1. Most of the rest of the halogens have an oxidation number of -1. All the rest of them are assigned based on the sum of oxidation numbers being equal to the charge. So you use these few always cases. You look at the overall charge, you sum them up, and you can assign the oxidation numbers of the other component. So let's do a few examples. So here I have set up a few simple examples where we're going to assign the oxidation numbers. Now the first one is water, and in that case, water, the hydrogen is bonded to a non-metal, so it's always +1. Oxygen is always -2. That's not a peroxide, so we have 2 of those, and that sums to 0. So those are my 2 oxidation numbers. Hydrogen's +1, oxygen is -2. If I had a reaction that changed in any one of those, then that would be an oxidation or reduction. Okay, now we go to ammonia. In this case, nitrogen is not one that we have an automatic assignment for. So let's look at hydrogen, which we do. We've got +1. That's its oxidation number. Okay, the oxidation number of each of the hydrogens is +1. And we have 3 of those, so that's 3 times +1, so it's +3. So nitrogen must be, in order for this whole thing to be neutral, -3. So there are my oxidation numbers, and that's summed to 0, which is the same as the charge. Now let's look at MnO4 minus. Okay, that's squiggly minus, but that's okay. In this case, manganese, we don't know. It's not one of ours that automatically has an oxidation number, and actually it's a transition metal, so it can often have lots of different oxidation numbers. So let's do -2 for our oxygen. Now we've assigned half of them, but we have 4 of those, and -2 plus whatever manganese is equal to -1, because notice the charge was -1. So this is -8, and so what must the oxidation number of manganese be? It has to be +7, and that sums to -1. That's how you assign those oxidation numbers for those 2. Now we go to our last one, which is one of our strong acids, is sulfuric acid. So here we have 2 components that we can automatically assign already. We got -2, we got +1, and now we need to do a little math, because we've got 2 + 1 + 4 times -2 plus whatever that is equal to 0. Okay, so this is 2, that's -8. And then what would this be? This must be, so sulfur has to be +6. So +6, and that all equals 0. And those are our oxidation numbers. So it's actually pretty simple to do. You just have to identify the ones that are, the elements that are specified in that particular rule, assign those first, and then use the overall charge to assign what's left. Now that we know how to assign oxidation numbers, let's see how we use them in our deductions. So basically, if an oxidation number of an element increases, that element or the polyatomic ion or compound that's involved with is being oxidized. So in our example, our iron had a 0, and then when we assign our oxidation number in iron oxide, it's +2. So the oxidation number is increasing from 0 to 2, so that's being oxidized. The oxidation number of the element decreasing, then that element, or more importantly, the polyatomic ion or compound that element is in, is being reduced. So O2, the oxidation number of oxygen in O2 is 0, and then the oxidation number of oxygen in iron oxide is -2. So it's going from 0 to -2, it's decreasing. So here are our key takeaways. We've reviewed the concept of oxidation and reduction, and we've learned how to use or how to assign oxidation numbers to know if something is undergoing an oxidation or a reduction in our reaction. So until next time.